Okay, in this short video, I'm going to introduce the hyperbolic trig functions. First, let me show you a need for them. Let's say that you were told that y double prime was equal to y, or something like that. So it turns out that this would show up quite often in physics or in other things. So if there's a negative here, it changes things a bit, but let's say that this is just y double prime is equal to y. So you're thinking about this and you're like, the second derivative and the function are the same thing. I wonder what the function is. Well, it turns out that one solution would be e to the x, right? And not just e to the x, but anything times e to the x. Right? For example, 5 e to the x does hold this property. The derivative is 5 e to the x. And the second derivative is 5 e to the x. So it seems like 5 e to the x is a legit solution. But that's not the whole story, see? E to the negative x also works. E to the negative x. Watch, let's say if 5 e to the minus x, and you found the derivative twice in a row, you'd be right back where you started from. Okay, so y double prime would equal the original y. Alright, so what we're noticing is that both of these answers seem legitimate, and there's no reason that the c's have to be the same. For example, in the first equation c could be 2, in the second equation c could be 5. But here's the part that isn't obvious at first. If we added these together, you would have basically, again, a solution. So I'm going to put y general is c1 e to the x plus c2 e to the negative x. Okay, now, you can see how e to the x and e to the negative x could often come alongside each other. Now, in the special case, when c1 and c2 are the same number, that's when we get excited. So when, let's say c1 equals c2, then we get something like this. You don't need subscripts anymore. And you could just pull out the c. All right. So notice that this function here provides a real general way to think about functions whose second derivative is equal to themselves. Okay, so in other words, this just smells like y double prime equals y. Now, is it the only solution where y double prime is equal to y? Let's not worry about that right now. It's definitely a solution, right? So it turns out that mathematicians caught wind of this a long time ago, and they decided to give this a name, okay? This here. So in the special case, when c is exactly 1/2, so I'm not going to explain why, but if c is exactly 1/2, then we say that y is equal to this special case. And that function has a name. This thing is called cosh x. So why is it called cosh x? Well, it's kind of silly, but if you look at its graph, it looks nothing like cosine or anything. So, but let me show you why they didn't put like sine h. You'll notice that cosh is a nice even function. Okay, I just graphed it on Desmos, cosh. I have all the others turned off right now. So cosh is a nice even function. So it probably makes sense to call this cosh x, not sinh x. If you'd written sin hx, then it would have probably been more representative of like an odd function. So this is called a cosine hyperbolic, or hyperbolic cosine x. Okay? Now you might say, well, yeah, I see why they chose, cosh over sinh. Like, I'm glad they didn't use sin because then it might smell like an odd function. But why did they use trig expressions at all to talk about this? Like, why would you ever want that? Okay, so the reason they chose the trig prefix here is the following. If you define now that e to the x minus e to the negative x is y equals sinh x, sin, there's no c, it's sin x, but we say sinh x. If we define this now these two together, cosh and sinh, operate beautifully, okay? They operate beautifully, so let me show you. So check this out. Why would we use trig prefixes? Why not just call this like even, you know, new guy, and call this like odd new guy? By the way, let me show you the graph of sinh so you can convince yourself it's odd. There's sinh, odd function, see it? Okay, so cosh and sinh are these two new functions. They're brand new, they're odd. They both pass through different points that we're familiar with, like 0, 1 and 0, 0. Those are very familiar points. And so we like these new guys, these new functions, but why did we use trig prefixes? We still haven't answered that. Okay, so here's why. Let's see what happens when you take the derivative of cosh. In other words, you take the derivative of 1/2 e to the x minus e to the negative x. Oh, sorry, plus. The cosh has the plus in the middle. Okay, so what happens is the half pulls out. And then you basically get e to the x plus e to the negative x times the negative 1 from the chain rule. So that when you derive this term right here, you get minus e to the minus x. But see, this is sinh. See that? This is sinh. So it seems like one of the interesting properties of our new functions is that when you find the derivative of one, you get the other. This is one reason why they decided, hey, we better use trig prefixes, because that looks just like when you derive, you know, cosine, you get sine kind of thing. Okay, notice it's actually positive. The derivative of cosh, you might have expected to be negative sinh. And because, you know, cosine works that way. You find the derivative of cosine and you get negative sine. Here we found the derivative of hyperbolic cosine, we get positive hyperbolic sine. So this is our first relationship between our new functions that makes us feel like this isn't too far removed from the idea of sines and cosines. And by the way, I'll let you verify this one. Take a moment and do it. The derivative of sinh is negative cosh. So you probably should go ahead and verify that real quick, this green one. Not hard to do. Okay, let me show you another reason why hyperbolic trigs are considered trigs of any kind at all. So you remember the old rule that cosine squared x plus sine squared x is 1, right? It's ancient Pythagorean theorem is what it is. On a unit circle, any point is at cosine angle, comma sine angle. And those double up in meaning as sides of a triangle. And since it's a unit circle, the Pythagorean theorem alone represents this statement, doesn't it? Okay, so let's see what happens with hyperbolic trigs. Take a look at what happens when we take cosine squared. Okay, so take a look at cos, hyperbolic cos squared. So if you take this function and you actually square it, watch this. You get a 1/4, you get an e to the 2x, plus a 2e to the x, e to the minus x, plus an e to the negative 2x. So I use the a squared plus 2ab plus b squared rule there. Okay, so by itself, that's not very interesting. There's not much you can do with it. I guess you could take this e to the x, e to the minus x product and say that that's uno, because that's really just 1, isn't it? This is e to the x times 1 over e to the x. Okay, so but by itself, you basically just get this, e to the 2x plus e to the minus 2x plus 2. Now watch what happens when you take sinh squared, cosh squared and sinh squared. So this is very similar, except it's a minus between my exponentials. Oops, sorry, handwriting sloppy. This one's the same basic idea. You just end up with 1/4 e to the 2x plus e to the minus 2x minus 2. So I'll skip the gory details between here, but the only change is the plus here in yellow becomes the minus here. Okay, so what's really interesting is when you take the combination of the two. So if you take cosh squared and sinh squared and you kind of put them together, you know, add them, subtract them, play around with them a bit, let's see what happens. Well, if you take cosh squared x and you subtract sinh squared x, watch what happens. You get a 1/4. Sorry, spam call. Let me give myself a little more room. Sorry, you don't have to erase yours, but I needed to. Cosh squared x minus sinh squared x. So let's just take a quick look at that. So you would do 1/4, and then you have e to the 2x plus e to the minus 2x plus 2 minus, so that's this minus. And then we had 1/4 e to the 2x plus e to the minus 2x minus 2. So this is cosh squared. We wrote it down above. This is sinh squared. You can pull the 1/4 out, like all the way out of both brackets. And you have e to the 2x plus e to the minus 2x plus 2 minus e to the 2x minus e to the negative 2x plus 2. And basically, these cancel out, and you get a 4 inside. Interesting. You get 1/4 of 4, which is 1. Okay, so this is, I remember the first time I saw this, I was like, whoa, that's crazy, right? Because it seems like this e to the x business carries some semblance of sines and cosines knowledge. See what I mean? It's almost like something fishy going on here, even though our new functions here aren't really trig related at all. They're e's, for crying out loud, right? They're e's. They hold some properties that trig functions hold. For example, going back up, because we saw it earlier, the derivative of one is the other. What? The square of one minus the square of the other is 1.0. Like, that is so interesting. And the list goes on, and there's a tight relationship between the hyperbolic trigs and the trigs, even though we know very well that sinh and cosh have no actual trigonometric look to their graphs. They're not periodic functions. For example, you can't say that cosh of 9 is the same as cosh of 369, right? So we know like cosine of 9 degrees is exactly the same as cosine of 369, which in turn is the same as cosine of 729, right? Sorry, sloppy. That says a cos 729. And e's just don't work like that, right? They just don't. And we saw the graph of cosh. Graph of cosh looks like this. It's not even periodic. It doesn't even repeat itself. It's just like this parabola-looking thing. Passes through 0, 1. So cosh of 9 is definitely not cosh of 369. And yet, magically, we see these tight relationships between them. Interesting, right? Makes you wonder, like, if there's a deeper relationship between I and E and X and, I and E and cosine and sine and sinh and all that. Like, what is it? And it all really ties together beautifully in this formula. E to the IX equals cos x plus I sine x. That formula right there is a powerhouse, and so forth. So anyway, I don't want to talk about that too much right now because I know I promised this video wouldn't be too long, but I thought that's kind of a neat teaser. Like you find that basically you'll find that these are actually useful tools. For example, let's say you're working in some crazy problem and you run into this situation, x squared minus y squared equals 1. And what you might want to do is, let's say you forgot that this is a, you kind of haven't really studied this in a while, and you kind of forgot that this is a hyperbola or whatever. You could actually replace x with cosh and y with sinh. So in other words, probably don't want to use x, but maybe you could pick like another letter. So like a parameter. You can say, let's pretend x is just a cosh t, and y is just a sinh t. Well, it turns out that this statement is true on its own, as we saw here a minute ago, as well as a great new representation of a hyperbola. So if you graph like, this sort of thing, you're going to get a hyperbola. But it just means that we can totally redefine even the conics using sinh and cosh. So wait, is this the graph of x squared minus y squared equals 1? Or is it the graph of cosh squared t minus sinh squared t equals 1? Like, which is it, right? So it's a nice overlap. And physics often has diff EQs that solve to give you e to the t's and e to the minus t's. And now cosh t and sinh t make great replacements for those sorts of things. Oh, last comment. What is tanh? I'll bet you could guess. What is tanh? Well, it's sinh over cosh. So now I'll show you a picture of all 6 graphs. I already showed you a couple, but if you just type cosh x, this graph is so famous, you get a nice graph right there. Okay? Sinh x is an odd function version similar to the original. Tanh almost looks like arctan, doesn't it? Almost looks like arctan. Arctan, has a highest y value of pi over 2. Remember that? But look, this is highest value 1. So it's not quite the same, but it's a similar idea. And then of course you could even define inverses or reciprocals. So you could say like sech. That's hyperbolic secant. And cosec. I don't know how to say that one. Cosec. And coth. Coth is cool. Coth x. And some of these, it's really cool, but some of these don't even look like each other. You know what I mean? And I guess that's expected, but like this one here, this coth, it just looks like kind of like 1 over x, but it's not the same. Notice it doesn't actually have any range between -1 and 1. It's dead zone between -1 and 1. That's kind of interesting. Sorry, another call.